So we will continue on this linear quadratic setup. Last time we have seen the framework without min-field. So this time we'll try to include some min-field terms and see if we can extend the same technique to min-field games and then to min-field type games, and with arbitrary number of agents. It could be finite in finite number of players as well. So how does this work? I need the USB key. So I will start with the model of Jovanovic and Rosenthal of min-field games. It's really min-field games, and we will really look at in details why is that a min-field game. And it's a dynamic one this time. It's not static, based on Shapley's model. And then go back to my setup. Okay. The last part of the talk will be on inclusion of common noise, which are known to be more complicated PDEs. But can we solve that with basic techniques without using any PDE on it? So this is the agenda. After 1 week, after 10 days, we all know what min-field games does now, right? It's try to capture how infinite number of decision makers are going to behave. But in general, it's difficult to predict how people are going to behave. We cannot predict if you have only one single person. Now we are expecting to do a theory for arbitrary number of decision makers. So it's involved several assumptions, and one of the assumptions is rationality, right? How do you know if people are rational? This is a very difficult thing. We design models, we run them, and we expect them to behave that way, but actually they do something different. So there is something missing in our model. So we keep adding some other parameters, so on and so forth. So min-field games is not there yet. We need to add more things if we want to capture what is going on in the application side. So Jovanovic and Rosenthal, they proposed this model. Time is going to be discrete. So for those who are working on continuous time, for a few minutes, we will be focusing on the discrete. There is infinite number of decision makers, and I don't tell you what is this set. It could be diminuable or not. Each agent, each generic agent, pick up a control action, U, and U belongs to a constraint set. Okay? Your control action might be constrained by where you are and what is the population distribution. This M1 is the population distribution of state, location distribution. Right? S is the state, M1 is the distribution on the state of all the agents. Okay? So your choice is constrained by this set. For example, if you are in a crowded area, you couldn't move, it's because the crowd is around. Right? This is constraint. Now, how the state changes? Well, in his model, the next state is given by where you are, so the current state, what you are doing, and a min-field object. That min-field object includes the per state action. Okay, if you go to page 3 or 4 in his paper, you will realize that. It's included distribution of states and actions together. That's the 88 paper. Now, this is the dynamics of the states. It's just Markovian structure. Then that agent, that representative agent, get this payoff. So the payoff function depends on time. Time is t. The states, the action, and then the distribution of state and action together, this object here. Okay? So your payoff function depends not only on the state action, but also on the distribution of state and actions. Now, You can write the changes in the distribution through Kolmogorov forward equation, the classical one. We used to do it for finite number of states with matrices, multiply the matrix again and again. Here you have this operator that's a transition probability. You push forward and you get the next distribution and so on. So this is the equivalent of the Fokker-Planck. It's Kolmogorov equation forward because we know where we start. Now, the running cost, the long-term cost is with the discount factor in his paper. If you choose the same factor beta, then you get beta into the power t. You sum all the beta into the power t's. Beta is less than 1, you get 1 minus beta. So that's why you get this normalized form. So this is called discounted payoff. Beta is between 0 and 1. So that this summation makes sense. Okay? Now, that agent is going to optimize this object here. And you want to write down the optimality equations. So the one is already here, the Kolmogorov forward, where you plug the optimal state inside. Means here you will plot the optimal strategy inside. And the other one will be obtained through dynamic programming. So this is what he derived. He got the Kolmogorov equation, and he has the Bellman equation in this paper. It's a really meaningful game. Extended if you want, because the distribution of action is also there. I'm not going to, so he has shown that there is an equilibrium for this setup, mean-field equilibrium, subject to some technicalities on the continuity of those maps and so on. Okay. I will stop here for the introduction to mean-field games and give you more references. So last time I discussed about the relaxed control by Borel. So if your control space is not compact, you mixify, you complexify it, and now we call it relaxed control or mixed strategies. So those mixed strategies was introduced by Borel in the Colonel Boloto games. Lotka, Volterra, you are all familiar with this, like population dynamics, right? Predator and prey. So that one you can find here. Location, facility location games. The same we do with optimal transport nowadays is from Earthlings works. And the von Neumann references was already mentioned by Tamer Bashar last week. And then in the engineering community, we usually consider wardrobe equilibrium because in the context of transportation, if you have large number of drivers and over the road network, he defined the concept of, well, the Nash equilibrium as if you are using any of this road, if any road is used, then the travel time on that road is the minimum travel time. So that's Nash equilibrium, but with infinite number of decision makers. So those are static mean-field games. If you want to interpret as mean-field games, this is going to be static mean-field games. And then dynamic mean-field games, as I mentioned, the previous references. That's a really dynamic mean-field game, time-dependent mean-field game, if you prefer that. And several recent extensions of this work by Wintrow, Wincott, and Van Roy in 2005, and more recent. So this is somehow another community, but they are doing the same thing, if really the same thing, in terms of equations at least. Then continuous time mean-field games, I didn't look at in the details, but you have enough references for the continuous time mean-field games from part. And so the common assumption and the key difficulty is indistinguishability. You could relax it, saying that it will be indistinguishable within a class. That's what we call indistinguishability per class. So inside a class, they are indistinguishable, but they are interacting with other classes and so on. Now you can say, okay, I can make infinite number of classes, and let's be reasonable at some point. And they consider large number of agents in each class because they want to do mean-field. I have a problem with this in terms of applications, and I'll tell you why. So some of these, so the references, of course, are incomplete. And if your name is missing there, then I thought about you. So your name is somewhere here. You can think that is there, okay? So we are now back to the classical model of mean-field games. Infinite number of agents. Each of them is generic agents, and a generic agent here is I, but somehow it became I. So the state of I is Si. Si moves with that speed, that velocity here. The velocity depends on where I is, okay, where you are. What I is doing, this is the control action, is alpha if you want this, U is alpha, and M is the distribution of state of all the other agents. All other agents in infinite region. And then there is a diffusion term. I just pick constant, well, it could be dependent on time. For the moment, this function of time only, okay? And then there is a jump term, so Poisson jumps. Why do I consider jumps? The reason is this. If you want to model things like this, you have seen several behavior like this. For example, in markets, the price jumps. If you stay at Wall Street for just half an hour, you will realize that, okay? Half an hour is enough to observe this type of thing. So you want to say this can be captured with Brownian motions. This other is captured with Brownian motions, this other as well. But this type of larger jumps, you want to capture this with Poisson. So that's the reason why we are interested. There is a motivation behind. It's not just to do a theory. So we add these Poisson jumps to model this type of situations. So you start with the initial distribution of agents, and each generic agent runs this type of object. And you want to optimize the long-term payoff. So that's cost function, terminal cost, and then running costs here. Mean-field equilibrium. Same definition as Jovanovic, no need to change anything. Kolmogorov forward equation coupled with the Hamilton-Jacobi, where the Hamiltonian here I'm minimizing, so it's L plus the drift term, the drift is here, D times P. P will be the gradient of the value function. Okay. You minimize this, you get the optimal control, plug it back here, and run this, you get your M star. That's the consistency check. The distribution of individual agents, we want it to coincide with this M star. So if you go back in the paper, that's already defined, but for discrete time mean-field game setup. Okay? Now, if I'm adding this term here, that's going to change a bit your PDEs because there is a jump. If we have problems in finding weak solutions, now with jumps, what happens? So for those who are fan of probability theory, you look at here. Those who are fan of PD, we look at down, okay? So this time I have everything for everyone. Probability theory, you go here, although you still have to solve something, but you go here, you derive stochastic maximum principle. So since I add the Poisson jump, the stochastic maximum principle is slightly modified with the martingale coming from the Poisson jumps. Okay? So my core states now are P, Q, and Q tained. Okay? The other part of the formula is identical, but there is a term here, J. This is for jump. This operator, so J star is the adjoint of J, and J is given here, is the jump operator. Now, Poisson jump has a intensity measure. That intensity measure here we are considering to be a random measure, means for all compact you get finite, the measure is finite. Okay? So the intensity measure of the n, the Poisson jump, is new. The n-tint is just the compensated version of it to make it rectangle. You want the expectation to be 0, right? So if you have a Poisson process, n, we know that n minus lambda t is going to have to be a rectangle, right? So this one is what I call n-tint. It's just making it centered. So that's the mu here appears when you do the jump. You want to do the variation. In the variation, the second order variation here, you get the jump operator j. Now this j appears in your Bellman. Okay, you take the old Bellman, the Bellman you have been doing last week, and now you add this jump term. It's a linear operator in V. And that's your new Bellman equation. The proof is very easy. We just use Ito to establish the same thing. Okay? Now, this is what we call integral partial differential. So PID, this integral partial differential. Integral is because of the integral here over this term that appears in your PDE. But it's linear in V. That's good news. It's linear. It's linear. This operator is linear. Okay. Now we have to solve this. We have to study the existence solution of this new system, or if you prefer, we have to solve this one for those who are doing maximum principle. Okay. So in the linear quadratic case, this two becomes much easier. I will take my answer, plug it here, and identify the coefficient and show you that they are identical to the direct method that we are using to check that the solutions are the same. Okay? So I take my the linear quadratic problem, I plug in this PDE because I have an answer for V. I plug it inside and I identify the coefficients. You'll get the same results. So that's your first exercise for today. You could check that the solutions we are going to get are really solving this PDE. Some references about the existence and uniqueness. One is jump-free, means you remove the jump terms. You already know those references. But if you add a jump term, it's more involved because of this operator that is added to. It's the adjoint operator. So you need this is linear operator. You look at the adjoint operator to it. From Bellman to Fokker-Planck, we do the weak formulation, integration by part, right? You do that thing here. Any question on this? That's Minfield game, so you should be happy to. Okay, so let's move on and try to apply this Minfield game in context of evacuation, but not only ground floor, because I used to travel a lot, so sometimes I go to places like Hong Kong or Dubai or New York. So sometimes you want to do evacuation of a tower, multi-level building evacuation, not just I have a ground floor, I want to evacuate that. Okay? Then the difference, there will be a difference because there are people who are at the upper layer, they are going down, so there is a new flow coming into the picture. If you write down your Fokker-Planck, now there is external flux coming from the other floors. They will be added to your Fokker-Planck or the ground layer. So you write a distribution of agents for each floor, and they are taking the stairs to be evacuated, to go down. Okay? There is a paper on it in details. So this is the Dubai Tower. It has 163 floors. Imagine you have to do all that walking. 163 floors and 828 meter high altitude. The ground floor looks like this, just the map of the ground floor. There are a lot of exits, so that's good news. Whenever there is a problem, you could exit in one of those are the exits. Although some of them might not be working. So the lower level here, this is an hotel, Armani Hotel. And then you have offices, commercial part, and there are some other part that I don't know the details. Okay, so imagine you are part of this hotel and people like Tambin want to test evacuation for you. So that might create problems, and this is why we get interested in this. So this building has specific properties. The dynamics for evacuation is not necessarily down. I didn't tell you that. So sometimes, depending on your location, it's better to go up, and you'll be evacuated from the upper layer, because here you go. Those blocks are evacuation areas. So if you are at the 18th floor, so this is 0 to 25 floor, 25th floor. So if you are here, it's better to go to this area, and you'll be evacuated here directly through the sky bridge. But if you are somewhere here, maybe you want to go down. So this has a specific structure. You don't have to go down all the time. Otherwise, you have to do 163 floors. Okay. So that's why the dynamics you see here. So if you are here, you go down. If you are there, you go up, and so on. Okay, you can solve your PDs, and you realize that it has to do that as well, because you are looking at shortest path or congestion with shortest path and so on. So what I have to solve is some kind of econol equation, but in 3D. Okay, the model is simple. It's just x dot equal to u. I think you cannot do simpler than that. X dot equal to u. There is no, those who are working in physics, they look at acceleration. It has several terms, this type of forces, that type of forces, and so on. Since I don't know anything about physics, I do x dot equal to u. Just that. Now, there is a discussion on how can you choose your speed, because in practice, you can change your acceleration, but speed comes as consequence. It's not something that you could choose. And here I want to control my speed. So that's the issue with my formulation. Now, you want to optimize this cost functional. It's quadratic in U, but not in the state, because I want to capture more congestions there. Okay. So quadratic in U, small modification from my framework that was, I promised to be quadratic all the time, but sometimes I slightly add to be more realistic. Okay? Instead of looking at the density, you look at the people who are around you. That's not density, because if you are located somewhere here, you occupy a space, okay? Epsilon. You cannot twin down this to 0, because you cannot compress people, okay? At some point, you get closer and closer and closer, your epsilon cannot go to 0. So you count how many people are around you. If that number exceeds 4 or 5, okay, that's big for me, okay? 4 or 5 people around you between 2 meters, okay? Here, around. That's how I measure congestion. So I said it's crowded if I have 6 people around me here. That's crowded for me on my location. Okay? Now, if it's crowded on my location, this G I will define next will be high. And if not, it will be low. And you could move in classical econol equation. There is extra term that was to get some fancy things related to meaningful games. So the cost function will be a terminal cost like this, and then a running cost with extra value there. And the dynamics is x dot equal to u. Okay, I'm in a building, there should be some constraint. Otherwise, people will start bombing the walls and so on. I don't want to do that. So there are some constraints, of course. You need to stay inside the building, D, until we find one of the exits. Okay? Don't try to go through the windows and so on. No, I don't do that way. No, it depends on the congestion. So if it's more congested, so it's not symmetric if you want. So if there are more people downstairs than upstairs, maybe it's better to go up, although you are much closer to the downstairs in terms of distance. The number of people who need to be evacuated matters. The congestion matters. Right, that's right. But it still depends on the congestion and the energy you allocate. So in terms of constraint, I'm putting here. So if you take some directions, you need to change this control law to capture saying that, okay, if my direction is to go up, it will be more costly than it's going down. It's captured in the previous model atlas. Right? No idea, because people will not tell you if they are going up or down. You just go there and you realize that it's just crowded. So right now what we do, in terms of design, we will send them information, right? But that's not included in the model here I'm presenting. So you can design the situation saying that, okay, over the screens, or you need to send them information online. So this is just counting how many people are around you. So this is I. It has a certain comfort zone, whatever, a certain range, epsilon I, and you integrate your measure. This measure is what I defined in the previous. It's the sum of the Diracs except I. Okay? So now I am in your setup, except that it's discontinuous. This object is, there is an indicator there. That's the only difference. If that function here was smooth, or with some kernels, then you could do C as convolutions, and you could use the previous theory. So the difference here is that you get some not nice object. You could convolve with some nice things there, if you prefer that. The PDE associated to the constraint meaningful game, constraint because you are playing on a domain D, correspond to this. The Hamiltonian is because it was quadratic in the control, you could compute explicitly, you get this Hamiltonian. This is the Bellman equation. It goes backwardly. Well, I forgot a meaningful term there. Okay? So that's the Bellman equation, and this is the transport equation. HP means the derivative with respect to the second variable. Yeah, that. Okay. Yeah, no, I took Neumann. Yeah, Neumann condition for the boundary. Well, you could look at other type of conditions, constraint, but here is I took just Neumann. And except the exit, of course, they have to be evacuated at some point. For the exit, you need to design the K function. Okay. So what do? We look at from where you are located. You look at where there is any exit. Look at your evacuation plan. How many doors do we have here? Okay, at least 2 should be there. And they should be working in case of why we need at least 2? Yeah, or for security reasons, if one of them, if there is only one. Okay, so if there is only one and the security issue, that one is blocked, then we are all stuck. Okay, so you can add a diffusion term. Okay, from the previous dynamics. If you love stochastic things, you could add some diffusion terms. But for the building, I don't recommend you that. I can recommend you to solve this system. But if you want to apply this to evacuation problems, adding a Brownian noise to somebody who is close to a wall, for example, it says it can go in any direction because of the Brownian. Is that what you want? You will see some people changing their direction and coming back, opposite direction, even with small diffusion coefficient. So this is not the one that we implemented. What we implemented is the previous one. Okay. We do this, and if you want to see this as a noise and look at perturbation measurement in the speed, you could look at that as a deterministic system, not as a random walk. Okay. Now we run it over 163 floors, but the videos are for each floor, so I couldn't show you here. But in the paper, there is a paper, that one. You have some of the illustration of the 163 floors. So I'm going to take another example where it's easier to show you on screen. So floor 1 and floor 0. Well, okay. I don't know which one is. Okay, this is ground floor. There is an exit, 1. And this is second floor. And the evacuations, so in this area, you see that depending on the number of agents, some of them are exiting this way and some others are going that way. So this is what happens if in the multi-level, depending on the exit zone, evacuation zone of the higher floors or the lower floors. So these guys on the second floor, they are all taking the stair here. This is the stair, and they exit here. Okay, they enter here, but they exit there. The red one is where they are going. You see some flow coming down. Okay? And then they all get evacuated. Right? So what do you do? So if M is given, just solve your equinal equation. It will tell you this is the direct way to go. But then you compare with this exit to that exit and that exit. Take the minimum one and go there. It's pretty, in this case, we know the solution of the equinal equation if M is given. Now, M is not given because M is the number of people who will be around me in the future or now. So I had to compute the system back and forth and stop at some point. Right, you solve the meaningful game, and you get your optimal control and tell them they apply the optimal mean field equilibrium, but the system is finite. It's epsilon Nash if you prefer that one, but I have no proof that for deterministic system like that is epsilon Nash. I have no idea. But they are implementing the mean field control, mean field equilibrium strategy. It's not the Nash equilibrium for the finite game. But if they are going to the shortest path, I am happy. I know that Nash equilibrium has this type of property in equilibrium. Okay. This was done for 200 agents agents in each floor. I mean, here we are only 2 in the illustration. But in the other building, so in total, we have 50,000 agents because Dubai Tower, together with the Dubai Mall, has 35,000 agents, people, but 50,000 in peak hours. Okay. So the mall is the biggest in the world with 1,500 shops and so on. You could look at online all the details. So now in some cases, you might need to add another dynamics, another mean field equation for smokes, flames, and so on. Probably Professor Yan can tell us what is the flame dynamics. Then couple this with the density of people. So if you go to a place where it's crowded, or to a place where you have a lot of smoke, you want to avoid those places because smoke and crowd are now enemies for us. Okay, you don't want to go to a stair where it's already smoked. I mean, a lot of smokes there. But that dynamics is external. It's driven by physics law and it's influencing our decision. It's external dynamics, but I use that in my decision because it matters if I cannot get any oxygen, anything. Now, end of the application. We are back to basic setup without the coupling with the state and the control law. Right. So for econol equation, we have the fast sweeping method that's already known. It's econol equation, the one that we are using in this application. It's not a general numerics. Right. That's known for any problem with shortest path, right? So computing shortest path is already well established framework. Numerics is there already for this specific problem. So the scheme that is used here, the numerics is detailed in the paper. Is not extendable to any meaningful game problem. It's just for this problem. I mean, for any problem with the shortest path. Right? It's limited to that. Well, you might extend, but I have no idea. So can we extend the direct method we have seen last time to mean-filled games setup? The answer is yes. And it's in that draft. I'm not going to present it because I will do meaningful type games. Okay? You can look at that in the paper. Now, but I will give you one basic example of meaningful game, linear quadratic, because I'm going to compare it to the meaningful type game. So here is the setup. Quadratic in your state. I is the representative agent. There is a meaningful term. This is the average state of all the agents. There are infinite number of agents. I mean, meaningful game. Okay? Average state of all the agents. Quadratic cost. Okay? These coefficients I asked to be non-negative. This other could be negative. And the sum of the two, I want it to be positive or 0. And you want to solve, so you want to solve you take the expected value of the cost and you want to minimize it subject to a state dynamics here that is linear in S. These are function of constant or function of time, but there is no state there. So it's just linear in the state and control term. Okay? You want to solve this meaningful game. The solution is your answer to be quadratic. You plug it there, identify the coefficient, and you find the solution. The solution, the optimal cost is here, where the alpha that appears here is explicitly given here, and there is C that appears here, and that C is here, with the Jump-Diffusion coefficient. So this is the explicit solution of the mean-filled game problem. The optimal control is given by minus alpha Si, where S is the state dynamics that is explicitly solved in the mean-filled regime. Okay? Everything is explicit here. Now, I will move from this problem to mean-filled type game and solve that one, and I will tell you what is the difference exactly. So if you want to implement the mean-filled control, what you will need is just the state. So that's called state feedback. Now, from mean-filled to mean-filled type, there are different ways to move from mean-filled to mean-filled type games. And I will give you at least two different approaches. One is the following. You start with the mean-filled game, and you add a variance of the state there. Mathieu is one of the experts on this. So add a variance there because in the portfolio literature, they are fan of variance reduction problems, mean variance problems, and so on. So add a variance of the state in your cost function. You want to reduce variance. Then because of the variance, you are not linear with respect to the measure. So in mean-filled game, we take expected value of the cost function for a generic agent. This is linear in the distribution of state of that agent, right? Expected value is linear with respect to the measure of that agent. Inside, you have minifield terms, but the minifield term is not the measure of that agent when you are optimizing. In equilibrium, it will be, right? So it's linear, but the variance will be non-linear in that measure. That's the difference. Okay? So in game theory, what we call expected utility, this was proposed by von Neumann, that's expected utility theory. This is risk neutral. If you go beyond the expected value, means variance, third order, fourth moment, fifth moment, and so on, higher moment, then you get non-linearity in the measure, and that creates more difficulties. Okay? So you can look at the details in the Markovich extensions. He considered the mean variance case. Now, if you put time and so on, this was done mainly by Boalem-Geish from KTH and his co-authors. The minifield type control problem, and with the expected value that appear, a function of the expected value, and optimality conditions for it, maximum principle for that. So that appears in 2009 or 11, or 11. And then extensions of this framework by the same the co-authors of him, and then Alain Bensoussan has a book on it on this framework. Okay, and the group by Mathieu and Olivier, their work on dynamic programming version of that problem and so on. So that's minifield type control. Now minifield type games takes the minifield type control problem, but with multiple agents, as in classical games. Could be finite or infinite. So minifield type control problem, but with more controllers. So we have seen the definition of minifield type game. We are back. You could include, if you don't like the distribution of control, remove just that, and you have a pair function that depends on your state, the control input of all the agents, the distribution of states, and control of all the agents. Transition kernel does similar thing. And we are interested in the variance, in quantiles, other risk, value at risk, and several other interesting things. So let me give you another example. Instead of evacuation now, we want to have a comfort temperature in this room. Okay. So we are in a building. We want a comfort temperature. For those who are from Sweden and Canada, I guess this is too hot for you guys, but but for those who are from from Texas, they might want to increase a bit. So there is a comfort temperature we want to fit in the entire building. And once you enter into comfort zone, that will be from between 18 and 23, let's say, degrees Celsius. Okay, that's Celsius. Then you want to reduce the variation, for example, from the center of that. So you want to reduce the variance once you are there. Okay? So variance term around this comfort temperature will appear. If you can see this from the AC, is there any air conditioning here? No? Okay, doesn't matter. So if you go in a place where you look at the air conditioning, it's trying to look at the variation, right? I start cooling when I see that it's going out of that. I start cooling because it's exceeding the upper bound, and I start heating if it's exceeding the lower bound, right? So you design it control such that you stay in that box all the time. Maintain the temperature in the comfort zone all the time. This is what you want to do. Now, this needs to include some variance terms. You could involve more other things, but some variance terms. So we have chosen the variance as a key thing for those things. We could look at quantiles, but it's more complicated, so we started with the quadratic one. So we take the variance, and we want to analyze the game. The same example as before, but now when you see M bar you replace it by expected value of the state. Okay? It's really the same example as before. But in min-field games, you freeze this, and you say this is the average state of all the agents. In min-field type games, you cannot freeze this. Why? Because you look at the state dynamics, you change your control, this is changing the state. So it's going to have to change the expected value. If it's changing, how can you freeze it? You cannot freeze this. Now, if you solve with min-field game approach, we have done it. Now we'll solve it with min-field type game approach and look at the solutions. This is a very simple problem. There is no, so the min-field type game solution, Nash equilibrium solution, its cost is here. The beta that is here solved this ODE. The alpha is the same that was appearing in the min-field game, the same alpha. C is exactly the same as before. C is here. Alpha is here. Okay? And the optimal control now is modified. Because you couldn't freeze, you need now to track it. You keep tracking it. Your optimal control depends on your state and the mean value of the state. It's still state feedback, but now it's augmented with the mean value that you need to track. Well, you might be able to solve this explicitly because it's given here. So then you just need the initial state and keep tracking with the initial state. Because the initial state will appear in your optimal control and the cost, this is called time inconsistent solution because you keep paying depending on where you start initially. So if the previous generation started somewhere, I am not part of that generation, but still I have to pay. That's time inconsistent. Okay? So the two solutions are different. This cost is lower than the cost in min-field games because the alpha here is much, the beta here is higher, lower than the alpha in the other one. I give a plot of it so that you see all the, this is the state. The other is a design for control actions. If you know a bit about control theory and how to implement this in practice, we design that way with the alpha and beta. So this is the cost in the min-field type cost, and this is the min-field game cost as a function of Q bar. Q bar is the min-field, the effect of the min-field type, I mean, the expected value part. Okay? So you see that the gap, there is a significant gap, even in this simple game, between the two solutions. People claim that, okay, I reformulate as optimal control problem, therefore there is algorithm and so on. But the solutions are different, and we are interested in solutions. They don't give the same. One is I freeze and I solve it. That's two-step method. First I freeze, I solve, back, forth, back, forth. Is that going to be the optimal cost? No. The answer is no. The optimal one is this. Okay? So I'll stop on this example. This is enough for linear quadratic. Now, can we generalize the direct method to include min-field type terms? Okay? Now there will be min-field type term, expected value of the state, and expected value of the control action. Okay? The drift is modified to include the expected value of the state and expected value of control action of all the agents. There are n agents here, n agents. Okay? We have a Jump-Diffusion on it. Can we solve this? You can rewrite this cost as the variance part because you can combine these two to get a variance term plus another term like that. So this is a variance reduction somehow problem. The explicit solution of this is given in this recent paper that is online. There we do the direct method. We do stochastic maximum principle. We do dynamic programming. We solve with the 3 separate methods and tell you what are the differences and so on. if you have time to look at the dynamic programming approach and so on. The solution is, so that you take this ansatz, alpha x minus s bar. S bar is the expected value of s, plus beta s bar square, linear term, constant term, and so on. Okay? And then you apply Ito's formula. And then you identify the coefficients, alpha, beta, and gamma, and delta. So the optimal control depends on your state, the mean value of your state, again, the mean value there. The average state is just linear, so there is an exponential decay for it. You have seen it in the plot. There is exponential decay. You want to drive the state to 0. The coefficients solve these equations. We have seen the first equation last time, the Riccati equation, alpha I coupled with alpha j's. Okay? There is another Riccati equation for beta. They look similar, but actually no, because this is A and this is A plus A bar. So this is coming from the mean field term. This is from the classical stochastic control. And then the other terms that are linear. These are linear in the Riccati equations. So you need to show that there is a positive solution to this system, which is relatively easy. In this case, you need to assume that this Qi is positive. We are minimizing a cost, so the coefficient that is there, positive. It's not really a big assumption for that. You need to assume that this is positive because the coefficient behind the quadratic should be positive. If you put negative, it's like the time, the same thing we have seen with the log last time. So you get finite time blow up if you put change the sign there. Last part. So I take the same problem, but this time there will be a common noise. I will add a common noise. We all know that the PD associated to common noise is somehow heavy. Can we do direct method? Find the solution, go back there and plug there and check that it satisfies there as well. Okay, so at least for the direct method, I'll give you here. So the expected value is now going to be a conditional expected value. It means it's a random variable. I mean, it's going to be a random variable. B naught is the common noise that will be observed by all the agents, all n agents. We keep the Jump-Diffusion term. We replace only the expected value of the control by the conditional expected value of control. FB naught denotes the filtration generated by the Brownian motion that is independent of the other Brownian motion that was appearing and the Poisson jumps. Okay? Now, direct method, remember, applies Ito's formula. There is no change from the common noise free to the common noise dependent. Small change in the Ito's formula, but no other thing. You plug the ansatz that I will give you, apply Ito's formula, and you'll identify the coefficients. But they are going to be stochastic because this object is changing the dynamic, the Riccati equations. So the explicit solution is given here. The cost structure is similar as before, but the coefficient now, this alpha, is not an ODE. It's now an SDE, means stochastic ODEs. Okay? The optimal control has similar structure as before. You need the conditional expected value of the state. This is what the conditional expected value set solve. So it's this SDE. Since you know the common noise, because we are assuming that you observe it, so each time you observe that, so this process is observed, sigma is given, so everything here will be observed each time. And you run this S hat, and you plug it there. Okay? That's the estimation process. It's just Kalman filter, if you are more familiar with Kalman filtering. Okay? I'll give you here. It's the Kalman filter. Now, The coefficients solve similar equation as before, no change here. It has to be adapted to the filtration generated by B naught. Well, here you could choose, with that terminal condition, you could choose this one to 0. Same thing here, this to 0. So these first two are ODEs, but the other two here are really SDEs, because you cannot set this to 0 because beta I is not 0, because beta I solve this ODE. So there is a really SDE part component on it. Okay? Now, while these are ODEs for us, well, if we modify a bit to put the diffusion to be dependent on the control, or the jump to be dependent on the control and the state, then this will be really an SDE as well. We have that extension. So let's summarize. If you add a common noise, you get an SDE, which regularizes somehow. Even if there is a blow up, it might help you to get solutions. Okay? You get coupled Riccati because you are in a game context instead of one single Riccati. We didn't use dynamic programming or maximum principle to solve this problem, but we have checked the solution using those with the master equation. You solve it and verify that, you solve this through direct method and check there that it satisfies the other PDE, the infinite dimensional PDE. That I will give at some point next lecture, the PDE associated to it. But I will not solve it. Okay? I stop here.